Good morning and welcome to the cable thermal analysis webinar, especially for underground raceway systems. My name is Tanuj Khandelwal, and for the next 45 minutes to an hour we'll walk through some of the capabilities inside ETAP for cable systems analysis. I'll be utilizing ETAP 14 for this purpose, so for those of you who haven't upgraded or haven't received ETAP 14, please feel free to contact us, sales@etap.com. As far as ETAP is concerned, we also send out newsletters. We are working on a new website as well with a new look and feel. And if you are not receiving our newsletter, again, please feel free to contact us, marketing@etap.com, or you can go to our website and subscribe to the newsletter and stay up to date with the latest news and capabilities inside the ETAP program. So the agenda for today is essentially to cover a little bit about the cable systems inside ETAP. We'll then talk about the graphical user interface, go through some of the analysis capabilities or analysis types, some of the features like rulebooks and wizards that we have inside ETAP, and we'll kind of cover some of these things with examples as needed. So first of all, when we talk about ETAP, especially the cable systems, when we are looking at cable systems, we are typically analyzing cables based on either their mechanical strains or stresses. So we essentially utilize a cable pulling module where we calculate the sidewall pressure and tension on the conductor. We can also do network analysis, so we can essentially do voltage drop calculations, short circuit analysis, motor starting harmonics, and essentially size the conductor based on different types of network calculations. The other aspect of doing cable analysis is essentially the thermal analysis. So that's where we utilize the cable raceway system, and we calculate the temperature and ampacity of the conductor. So when we look at ETAP, and we're essentially looking at an example file that is available with ETAP as well. And if I go to this particular conductor, cable 2, as you can see, I've already run a power flow calculation. I'm seeing some current going through this conductor, so I can easily turn on the voltage drop and evaluate the conductor based on voltage drop capability. I can go into my underground raceway system, look at that conductor, and actually perform a calculation and see the temperature based on the same ampacity. And I can also go to my cable pulling system, and I'm just going to bring it up right here, where I'm actually routing this cable through a manhole with certain bends and elevation angles, and I can run my calculation on the same cable too, and calculate the forward pull and the reverse pull tension, as well as the sidewall pressure as that conductor is being routed through the manhole. So this cable, essentially, which is cable 2, exists as a single cable inside the project, but it's essentially utilized by multiple systems inside ETAP. So whenever I make changes to the size on cable 2, and let's say I change it temporarily to size number 8, and I go back to my underground raceway system, you'll see that cable 2 is essentially size 8. And if I switch it back to size 750, click OK, we can see the conductor size increasing. And when I go back to my single line diagram, I can see that this size is now back to 750. So it's essentially an integrated system where the single line diagram, the cable pulling, and the thermal calculations are all connected together. However, you have the choice of utilizing each of these pieces individually or tying them together. Now, when we talk about cable installations, these are essentially the cable installations that are currently supported by ETAP. Obviously, not all of them are covered by every single standard. For example, IEEE 399 Brown Book covers underground, direct buried, and duct bank standards. The ICEA standard covers cable trays. The British standard, IEC 364, and some of the other standards, they cover other types of installations, especially commercial building related standards for low voltage applications, such as building voids and brackets and so on. So depending upon the standard you choose, if the standard supports certain installations, ETAP will essentially allow you to size the conductor based on those capabilities. So just as an example, I'm going to go ahead and again pick our cable 2 here, go to the Ampacity page, and you can see I have a choice. I can either size this conductor and calculate the duration or the capacity of this cable based on any of these applicable standards, or I can choose the installation type. And in this case, if I choose an installation type, then my standard list changes accordingly. So we've tried to put a lot of intelligence as far as determining, based on the voltage level, which standards are applicable, or if you choose an installation type, then which standards are applicable, and then we go ahead and provide options associated with that standard. So again, if I go ahead and pick the Brown Book method, as I was mentioning earlier, it allows us to size underground duct banks and direct buried raceways. And the Brown Book standard essentially may be used by multiple countries, or if you're using IEC standard, then again, there may be derivations of the IEC standard for other countries that are following 60502. Now you notice that this standard is for medium voltage because that's a medium voltage conductor. However, if I step back from this diagram and enter a low voltage network and pick a low voltage conductor here, then I can see additional standards such as French standard, NFC 15, BS 7671, IEC 60364. So all of these are applicable for underground duct installations. And if I've selected IEC 364, you can see these additional installation types here that I can utilize for doing cable derating. Now, I can obviously use the cable editor to do my cable derating and capacity calculation. So just for the sake of demonstration, I'll pick IEC 399 again. Quick standard, I'll pick underground duct. I have my conductor already, so if I assign this conductor to a duct bank where I have 2 rows and 2 columns, so that essentially implies I have a 2x2 arrangement, or essentially 4 conduits, 2 rows, 2 columns inside an underground duct. Then the program essentially will allow me to derate my conductor. So since I've already set it up for a 2x3 for cable 2, we can see the base ampacity is 530 amps. And based on a 2x3 arrangement, I can actually only push 300 amps through that conductor before I overload that conductor based on thermal capacity. So there are basically a couple of factors that are involved in cable derating if you're utilizing the ETAP editor. We actually consider duration based on ambient temperature. So you can see that the 530 amps was based on 20 degree ambient temperature, 90 degrees Celsius conductor temperature, and a 90 degrees Celsius centimeter per watt soil thermal resistivity. However, if I apply this cable in a similar condition, but in a 2x3 arrangement, you can see I still have a duration of about 340 amps. But if I apply this conductor by itself without any influence from any other conductors, I can essentially achieve the 530 amps base ampacity. So this is with the understanding that there are no other conductors within the duct bank. This is the only conductor that's there. But in real life, that is not the situation, and there may not be exactly the same types of conductors within the same raceway. What I mean by that is this particular size may be adjacent to other conductors with different sizes, with different voltage levels, and in that case the standards such as NEC or any of the other cable derating standards that we have here, they essentially hit their limitation, and we need to go and do a more detailed thermal analysis, and that's essentially where the underground raceway system essentially steps in. So when we are essentially derating the system, we look at the number and the size of the conduits, the configuration, the arrangement, horizontal, vertical arrangement, the depth of the conduits from the surface. So the deeper you go, we expect the soil to be cooler, but it takes longer for the heat to be dissipated as well. So depth plays a factor. You also have situations where you may have two duct banks or two conduits directly buried close to each other. The backfill makes a difference, and so does the load factor or the ampacity going through the conductor. So back to our discussion, which method should I use, the NEC type based method or a graphical UGS method? So if you look at NEC section 310-15B, I'm going very specific to US National Electric Code here. There are certain details that are mentioned, detail 2, detail 3, which are typical arrangements, a 2x2 arrangement or a 2x3 arrangement. So if the arrangement is very similar to the duration factors that are specified in NEC, you can essentially use the cable editor for derating that particular conductor. However, if you're using any distinctive or different duct bank arrangements, then we essentially fall back to Neher-McGrath or IEC 60287 thermal analysis method, where we essentially have full flexibility on which conductors are placed in which conduit and how they are arranged and spaced in the system. So when we're essentially looking at the thermal analysis, we're actually looking at the underground conduits or directly buried cables or cables buried in conduits which are directly placed in soil, any of those conditions. And these cables are either three-phase, single-phase, or DC cables, so we kind of cover all of those cases inside the program. The key is essentially to determine where do we take the cross-section. So when we are doing the temperature calculation, we are essentially telling the program we are placing cross-sections at different parts of the raceway, an existing raceway, or when we're designing a brand new raceway. So as you can see here in this picture, we have a 2x3 arrangement, but there are 3 rows and 2 columns. However, when we look at the cross-section of the same conductor, when it's being routed to a different location, perhaps a different switchgear or a different machine, the arrangement changes. So this conductor that's placed in the top left corner here may be the same conductor that's being routed through a different arrangement, and it may be the same conductor that's routed through a third arrangement. So it's important to obviously understand where the cross sections are to be placed, and if you have a long raceway, you may need to take multiple cross sections, especially if the configuration is different, such as in this case, or the elevation is different. So an example of the elevation is where you have a case where the raceway is being passed under a bridge, an overpass, or it's approaching a railway line and the duct bank needs to be pushed deeper into the ground to essentially go under the obstruction and maintain minimum clearance. So in that case, you may have exactly the same configuration cross section, however placed at different depth from the surface of the soil. So ETAP essentially allows you to have more than one cross-section for the same conductor. So again, back to cable 2, I can essentially go back to my raceway here. My duct bank in this case happens to be 10 inches below the surface of the soil. You can see the scale on the left hand side and on the top corner. This scale is in inches because the example I'm using has US units, so I'm using US units here. However, you can always go into the standards and switch from English to metric units and use centimeters or millimeter units instead. So I'm basically 10 inches below ground. This is my cable 2. However, if I go to another raceway here, you'll notice that I have a cable 2 here as well. Same conductor, same size 750. However, it's in a conduit that's directly buried in the soil, and it happens to be 20 inches or beyond below grade, essentially. If I go to UGS number 1, another cross section, different types of conductors, different soil, backfill, same cable 2, but buried deeper into the ground. So you can essentially analyze the same conductor in different configurations and determine which one gives you the worst case thermal values, and that determines the derating factor or the maximum capacity of that conductor. So when it comes to the user interface, as we've seen, building the raceway is pretty straightforward. I'll go ahead and create a new presentation. So this is blank. We can essentially drop in a new raceway as such, and I'm just going to zoom out here so you can see this better. And you can then go ahead and drop in new conduits into this raceway. I'll choose one that has a slightly better color here, so it'll be easier to see. And we'll go ahead and drop a conduit here, and you can essentially come in and add a cable into the system. So it's pretty much straightforward. You just drag and drop and place things into the network or inside this presentation. However, this may require a little bit of an extensive work in order to align things and get the spacing right. So in order to overcome that and make the process a whole lot simpler, you can actually click on the Raceway wizard and choose, let's say, a uniform raceway. I want a 2x2 arrangement. The conduit that I'm going to use is going to be schedule PVC 80. Let's say the trade size is size 4. So that gives me an outside diameter of 4.5 with the thickness of 0.3 inches. I'm going with a center to center spacing, which is NEC standard of 7.5 inches horizontal and vertical. I'm essentially going to go ahead and just drop this raceway in. So you can see very quickly I have a perfect arrangement with 7.5 inches center to center spacing horizontally, and a 10-inch margin or spacing from the center to the edge that I had chosen, and that is all variable. You can change these however you like, and then I can just simply go in and do the same thing, drop my conductors in and start populating this raceway. So you can actually put in conductors as such or delete them by just clicking on the delete key. Or another way of placing conductors into the system is by going to the single line diagram, and here's the cool part. You can actually just drag and drop the conductor into the raceway. So in order to drag and drop, you just choose the conductor that you're interested in, and I want to go ahead and pick cable main, so I'm selecting it. I'm holding the Control Shift key and then just dragging this conductor. You'll see my icon is representing a cable. It has an X on it because it says you can't drop it there, so you need to find a place where it can be placed. So I want to go ahead and actually drop it here, and as soon as I do that, it's dropped in, and here's my cable main, which is essentially linked to the same conductor. So again, if I go ahead and change the size here to a larger size, click OK, you'll see that it's graphically changed here as well. So it gives you a very good linkage from the one-line diagram to ETAP. And very similarly, you can go ahead and pick any cable you want from the single line diagram and bring them in. And just like the time current curves with protection relays and fuses, we make sure that if you change the size on the single line diagram, it's uniformly synchronized with wherever that particular conductor is being used, so you don't have to worry about manually going back and changing all these studies. On a side note, you'll notice that when I dropped this conductor in, it came in as two separate conductors, and this one came in as a single one. And the reason for that is this happens to be a 3-core cable. So phase A, B, and C happen to be within the same jacket or within the same insulation, and I have one of these conductors per phase. So I have a single phase A, B, and C buried inside this single jacket or insulation. However, in cable 14's case, it also is a 3-core cable, so I have A, B, and C within the same jacket. However, I happen to have 2 of these conductors per phase, hence I see 2 of them. So if I changed it to 3 and click OK, now I have 3 of those per phase. So I have 3 A's, 3 B's, and 3 C's essentially flowing through this or passing through this conduit. So I'm just going to go ahead and delete these for now and go back to the analysis side of things. So when we are running the calculations, we obviously have a toolbar with a number of buttons on it. Let's just summarize what these buttons do. The first one is essentially steady state temperature calculation. So that assumes or takes a certain amount of current that you specify, or it's calculated from load flow, and that's the current that's flowing through the conductor. And once the current is flowing through the conductor, we assume that current is flowing for an infinite amount of time, and then we calculate a steady state temperature. So this is a temperature over an infinite amount of time the conductor has reached steady state condition, and this essentially gives us the operating temperature of the cable. If we look at the next calculation, it's uniform temperature and Pasty calculation and uniform temperature calculation. So the uniform Ampacity calculation looks at the conductor that has the maximum temperature, or it's closest to its temperature limit. It increases the amount of current flowing through it, but it maintains a uniform profile of the current flowing through that raceway. It bumps up the profile over the base value and then tells you how much more capacity does the raceway have if you continue putting the similar type of current uniformly through the raceway. There's a uniform temperature calc that basically tells you what is the maximum capacity of that raceway, assuming that all the conductors reach their temperature limit. You can size the conductors based on temperature, and then there's also a transient temperature calculation that allows you to put a time varying load or a load pattern or load profile in the system and calculate temperature as function of time. And then we can obviously choose our display options, our reports, and plot. So we'll quickly go through each of these one by one, but it's a short summary of the analysis capabilities we have inside ETAP, UGS, or underground raceway system. I do notice that some of you have questions, and I'll definitely be getting to your questions and answering them right after this webinar. So keep those questions coming if I'm not covering them during this webinar. So I have a raceway number 1 set up here. It has a bunch of conductors in it. If I double click in the background, I can see that my thermal resistivity of soil is specified here as 90. Obviously you want to choose the resistivity of the soil based on your operating condition or soil condition. We assume that the soil is uniform because we are not looking at huge sections of the soil, unlike a ground grid system where The ground grid can be a couple of meters, or it could be hundreds of meters, square meters large. The raceways usually are not, the cross sections are usually not that large for the soil thermal resistivity to vary that much. So normally we put in a conservative number or the worst case number to give us a larger or higher temperature value. The ambient temperature is soil ambient. So again, we need to specify a realistic soil ambient temperature. This is not the air ambient temperature. And definitely the soil ambient temperature varies as you go deeper into the ground. So again, we want to take the temperature within 30 to 50 inches from the grade, whatever that temperature is going to be. We obviously do assume that the soil temperature will increase slightly as it goes towards the surface. However, again, from a conservative point of view, you can either take an average number or the worst case number, and that is going to vary based on summer or winter, or in some cases, some areas where you have months of rain, the water may actually drop the temperature even further. So the ambient temperature is again uniform, and it should be considered based on the worst case condition if you're designing the raceway, or use the operating value if you have an existing raceway. We have warning and alarm temperatures, so those essentially allow you to specify the alerts. So this warning is sort of level 1, that you're approaching a thermal limit, and the alarm is a critical alarm letting you know in the report and visually that you have reached or exceeded the critical limit, the critical temperature limit in the system. So if I go ahead and run my steady state calculation right now, you'll notice that I have the current flowing through the conductor and a temperature value shown next to each cable. So about 156 amps going through here, 81 degrees. You'll notice that 81 is larger than the warning limit, hence the conductors are shown in this magenta color. And this one is actually not at 90 degrees, but it's approaching 90 degrees, so it's still in magenta color. So if I took this external heat source and I brought it closer to this conductor, and I can double click on this heat source and specify its operating temperature as well. If I took this up to 120 degrees, let's say it's a steam pipe, so it's superheated steam past 100 degrees Celsius, and it's that close to the raceway, and if I rerun my calculation, you'll notice that not only cable 2, but there's a number of other conductors that are affected by this heat source. So we are essentially looking at multiple heat sources and the effect of multiple raceways within the same system. We are not just limited to a single raceway. So X and Y location makes a huge difference in the calculations within the program. So again, for sake of demonstration, I'm going to go ahead and move this away, and we expect the temperatures to drop slightly. A few of the cables are no longer throwing up an alarm. There's still cable 2 that's past 90 degree limit, so that shows up in a reddish color. So you have a visual indication that you've crossed the threshold. You have the ampacity that is being used for the conductor, and the calculated thermal values for each conductor. So that's the basic result from the program. You can actually even go to the edit mode, go to the display options, and ask the program to show percent fill. So it quickly tells you what is the percent fill, and if you're following NEC guidelines again, you may want to limit the percent fill to less than 40% based on your installation case or your local standards. So I'm going to go back here, run my temperature calculation. Now, where did I get the 120 amps from, and how do I change it? So first of all, if I go inside the cable, go to the loading page, I can see that the value was probably typed in here as 120 amps. I'm not sure in this example. If I go to cable 6 and I go to the loading page, I see 156. Either came from load flow or somebody typed it in. So if I go in here and change this to something like 200 amps, and we'll go ahead and make each phase about 200 or so, you'll see that the operating current is now 200. If I go ahead and run my calculation, I'm now using 200 amps and my temperature goes up to 106. What if I wanted to use load flow? So again, here's where the integration comes in. So if I go back to my single line diagram, let's find cable 2 again. I'm going to go ahead and run a load flow calculation. I have 103 amps here, and I go to my loading category. I'm going to temporarily change my loading to 75%. So I'm lowering it by 25%. Obviously, when I run load flow, I expect a lower current to be flowing through the conductor. Now if I go back to my Raceway and rerun the calculation again, you'll notice it's using 264 amps. So I've connected my load flow results to the ampacity of this conductor. So every time I run a load flow, either in design condition or operating condition, I can get a realistic temperature flow or heat flow through this cable as well. And the way I was able to do this is by going into the load flow study case, and I selected the option to update cable load amps or cable load ampacity. If this is not checked, then whatever number you've typed in as the operating current, the program will just use it as a fixed number and it won't change based on your load flow calculation. So again, you have a choice. Either you can link it to your power flow results, or you can manually type in a number. So that's essentially how we are picking up the ampacity values for doing our calculations. Now this is our steady state temperature calculation. Here's my result. I'm going to go back to my load flow case here and go ahead and switch this back to none. We'll go ahead and get our normal amps again, which was about 356. So when I rerun the calculation, we'll see 353 over here. Cable 6 was manually typed in as 200, and so that pretty much remains as it is. Now the reason cable 6 may not have actually been updated is perhaps cable 6 doesn't exist on the single line diagram. So if you noticed, if I go to my list here and I look for cable 6 and I ask the program find it on the single line diagram, it won't, because this cable was not connected with my diagram. I had actually just dropped it as a brand new cable just like this. This cable 30 doesn't exist on the one line diagram. So its current and its properties are manually controlled, not managed by the single line diagram. So that's why cable 6 did not get updated here. Now when I click on uniform ampacity calculation, what you'll notice is that conductor, I'll step back again so you can see it. Cable 6, 200 amps, 106 degrees, 353 amps, 102 degrees. So when I click on uniform ampacity, the first thing the program does is it finds the hottest conductor. It happens to be cable 6. It's going to drop the amps going through cable 6 so that you are below the 90 degrees C limit. But it won't just drop the amps in cable 6, it'll drop the current uniformly throughout the Raceway. So you get a little bit more realistic power flow or thermal flow in the system. So if I want to make sure that none of my cables hit my temperature limit, however I want to maintain the current profile, that means the cable going through cable 8, 6, 9, 9, 1, 3 and so on, the base ampacities are adjusted proportionately. That's when I would use the uniform ampacity calculation. So I'm essentially increasing or decreasing the current proportionately through all the cables such that my hottest conductor is less than 90 degrees Celsius. So that's what this result is giving me right now. I'm going to go back to steady state again. so we can see the numbers one more time. I have only 2 conductors that have crossed the limit, and there are some that have not even come close to the limit. They're just about 76 degrees Celsius. So notice what happens when I hit the uniform temperature calculation. Almost all the conductors are now either at or close to their thermal limit. This one's at 85, the rest of them are about 90 degrees C. So what this number is actually giving me is the value 262 amps, 120 amps. This is the maximum capacity of those cables, such that all the cables within this system are at their maximum temperature limit. So I can essentially pass 120 amps through cable 6, 262 through cable 8, and that's the maximum limit of current. And both of them will basically reach their temperature limit because they depend on each other. I cannot just keep increasing current in cable 6 without having an impact on cable 8. So this is essentially giving me the maximum capacity of this raceway, such that all the cables reach their maximum temperature limit. So that's our uniform temperature calculation. And then the other option, which is the transient temperature calculation, that, as I mentioned earlier, uses loading as function of time. So instead of using a fixed number, which is right here, 120 amps, what if I wanted to use a transient profile? So the program will actually use this section of the cable where you can specify a transient load profile either in seconds, minutes, hours, or days. And the situation for using this, or the use case for this, is if you have an emergency condition where you need to temporarily overload a cable because you need to keep some critical load running in the system, and there's been a failure in one of the feeders in the system, so you're basically moving or transferring load from one feeder to another on an emergency basis. Now all cables have a thermal insulation limit. When we say 90 degrees C or 105 degrees Celsius, those are essentially steady state temperature limits for the insulation, but all conductors have a published emergency rating, and they allow the conductor to reach that limit, which could be 133 degrees or in some cases even higher, for a specific duration of time and for certain number of times during the lifetime of the cable. So if you follow the manufacturer guidelines and you stay within the emergency rating, you can then figure out how much and for how long can you overload the cable under emergency condition. So let's take this example. I have this cable at 120 degrees amps. It's actually at 90 degrees C, so I'm going to go back to my steady state temperature again. It's 73 degrees steady state, so that's what we know already. And what we want to do is essentially, after 1 hour, we want to increase the current to 800 amps. So that's significantly larger than what it's currently operating at. So obviously we expect the temperature to increase. And then I want it to run at 800 amps for about 4 hours. And then I'm going to go ahead and back it down to 120 amps again. So it's basically a step profile on the current. The current is 120 for 1 hour, and then it's going to jump to 800. It's going to stay at 800 for 4 hours and then drop down to 120. So let's see what happens here in this case. So this happens to be cable number 8, and we'll go ahead and run our transient temperature calculation, and we come back again with some results. Now you'll notice that these results are a little bit different than our steady state value. So I'm going to go ahead and run steady state again, 73. I'm going to run this one. You'll notice it's 139. I ran a transient temperature calc. It's load as function of time. So what temperature am I seeing here? This is the worst case temperature. that was achieved during that load profile. So that's really what the result's telling me, that if my emergency rating was 133 degrees Celsius, I exceeded it for this conductor. So let's see, when did that happen? If you look at cable number 8, and I assumed that cable number 8 had is essentially the same current going through every single phase in the for that conductor. So I'm going to just pick phase A and look at the current here. So we can see that I'll just pull up the points so it'll be a little bit easier to see. And the fonts on my computer are set to a high number, the resolution is high, that's why you probably may not be seeing the text here. So let's see, somewhere about 139 or so, we're looking at about almost 4 hours into it, we do hit 139 degree C value. So we can essentially then go back to our profile here and say, look, I can't do this for 4 hours, or I can't push 800 amps for 4 hours. So either value can be limited. If I limited the temperature, the time to 3 hours instead, so same amount of current, but let's say for about 3 hours, and then I go ahead and run the same calculation again, you'll notice that instead of the previous value that I had, which was about 139, I'm at about 136. So iteratively, I can very easily go back and figure out exactly how much time can I push 800 amps through this conductor. So this is below 133 degrees C, so at least for 2 hours I can push 800 amps through this cable, even though its base ampacity is 500 amps. But you need to verify, obviously, with the manufacturer of the conductor what that emergency rating is for that insulation before you go ahead and use that value. So that's essentially how the transient program can be utilized. There's many other cases or many other examples how it can be utilized in the system. I'm just pointing out one specific application. So back to our analysis. So we covered some of the analysis types, and when it comes to the features and capabilities, I just wanted to summarize a few of them again for you, and then we can actually jump into some of the questions and answers that we have. When I built this Raceway, with one option, which was uniform, and I built a 2x2 arrangement, and it gave me this perfectly built Raceway in the system. But I have two other choices here, non-uniform and circuit level. So what exactly are those? So basically the next one, which is called non-uniform, is something that you would use to build a Raceway that looks like this. We are basically setting up a Raceway that has different conduit sizes. The conduit size is not uniform, hence we call it non-uniform conduit size. And the spacing between the conduits is governed by the size of the conduit. So the larger the conduit, typically the spacing would be larger up to a certain limit. The smaller the conduits, the understanding is the conductors are not carrying medium voltage or high voltage power. The current may be lower, so they tend to be a little bit closer to each other. And then there's also another consideration that we have to look at later on, which is the type of current or signal that's being carried, whether it's power or control or communication. So we'll cover that in a little bit. But here's a case where I just have power conductors, and they're different sizes because maybe they are for different voltage levels or for different size of equipment. So how would I build something like this? I have a 2-inch edge-to-edge spacing on my first row, and I have a 6.5-inch center-to-center spacing here. So let's just give it a shot real quick, what we would do here. So I would select non-uniform. the program then asks you to select a rule book. We provide a default rule book with ETAP that has different conduit types and the spacing associated between conduit to conduit. So first let's look at the size. Here I can specify which types of conduits do I typically use in my system. If you're not going to use metallic or PVC-A schedule, if you're just interested in PVC schedule 40 from the NEC, then that's it. Then you don't need to worry about any other conduit types. The program won't even give you those choices. If you use PVC schedule 40, what are the typical trade sizes that you use in your installation? If you use any of these, then you can check all of them. They're all available for you to pick and choose from. If not, you can limit yourself to certain sizes only, and the program won't even give you a selection of using any other sizes to build your raceway. And then the spacing rule is from conduit size to conduit size. So from between a 3-inch or trade size number 3 to another size 3, the spacing edge to edge, because that's the option I'm using right now, is 1.25 inches. And this is a rule book, so you're more than welcome to modify it. You can duplicate it and set up your own rules based on trade size. So this is just one method, and so I'm going to go ahead here and say I got one row with 12 conduits, and I'm going to use 1.5, so that gives me an outside diameter of 1.9 inches. And then I'm going to use subsequent rows all the way up to 5, and these happen to be, let's say, size 4, and that'll give me the requisite edge to edge spacing as well. And the rest of them, the rest of the rows, I can just go ahead and delete them. So you'll notice as I deleted them, I'm getting a nice preview right here, and the program's telling me this is what your arrangement is going to look like, very close to the previous diagram I have. I'm not being very precise here compared to that diagram, but just as a demonstration, I'm showing you the capability of the program to get something like this very fast, provided you put in the exact values. So I did pick the right trade size, I just haven't picked the right center to center or edge to edge spacing. So here I do have 2 inches, so I am using edge to edge of 2 inches right here. So if I go ahead and click OK, and you'll notice my icon has changed. The program saying tell me where you want to drop this. I want to drop it right here, so I click OK, and I have my small cables size 1.5 and size 4 right here. And then I can actually simply double click on my new cable if that's what I want to do, and just start dropping the conductors in. If you set up the default cable correctly, and the defaults can be set up here, if you set your default up correctly, then you can even limit the effort required to specify what type of conductor this is. Otherwise you'll have to go to the library, select the conductor in each case, and click OK. But by specifying the default cable, by going here into the library and saying this is my default conductor, every time you drop a new cable, the program will give you that default conductor automatically, and all you have to do is then just change its size if that's what you need to do. So there's a lot of different shortcuts you can use to speed up the data entry inside the program. So that's a quick example of conduit based spacing. So based on the size of the conduit, there's a rule book that decides how much edge to edge or center to center spacing needs to be maintained, and this is a user configurable rule book. You can have a rule book for your site, for your company, or for your customer if you are a consultant. The other type of spacing rules is based on source of electrical noise. So this is important when you're mixing various circuits together that are of different types. So if we have a circuit such as a circuit that's feeding thyristors, welding machines, control cables, fiber optic cables, neon lights, they're all sources of noise, or they are susceptible to noise. Depends on the situation. So if you have a digital signal for controlling a contactor on a motor, it may be susceptible to noise coming from the power circuits. So it's a reverse problem. But in some cases you have noise generated by the system that may affect your communication circuits. So there is a IEEE standard 518, very similar to IEEE 519 for harmonic standard. There's a 518 which essentially provides us cable spacing that we need to maintain in order to mitigate mutual interference between power circuits and control circuits or signaling circuits. So here's a quick snapshot of that standard. Not exactly every single detail is here, but it's a quick summary for us to understand. So we have wiring levels specified in 518 from 1 through 4S. Basically 1, 2, 3, and 4 are the main levels, and S are the special cases. So wiring level 1, for example, is used when you have analog or power circuits less than 50 volts and or digital switching circuits that are less than 15 volts. And here is a typical example: phone circuits, coax cables, fiber optic. They fall into this category. And any conduit that you have that has these types of conductors or cables in it, you can mark those as wiring level number 1. So I'll show you in ETAP how that can be done. I'll just build a quick uniform one here and drop it. Open up my conduit, and you can see here I can specify circuit level 1. What you will see here is we also allow you to define some levels beyond 4S, like 5, 6, 7, 8, in case you want to accommodate any custom or special circuits that are outside the 518 standard. So by defining the circuit levels for the conduit, it's easy for the program to distinguish or understand how to separate it from any other conduit in the system. So circuit level 2, for example, is for light solenoid switches, all the way into control circuits at 50 volt, 1 kV levels, but less than 800 amps. And then you have power circuits less than 1 kV for AC/DC buses, and 4S is a situation where the power circuits are greater than 1 kV, so medium voltage systems greater than 800 amps. So the standard actually gives us spacing from tray to tray, tray to conduit, and conduit to conduit spacing. What we are using inside ETAP is basically conduit to conduit spacing. So here's a quick example. I have a communication circuit here, but these two circuits or conduits that I'm putting here are power circuits. Then I have a COM again, a spare, a COM again, COMs again, spare. So if I want to set up an arrangement that has a mixture of various circuit levels, and I'm not really interested in based on the size of the conduit, I want to basically set up the system to mitigate noise or mutual interference in the network, then I can click on circuit level option instead. I get my rule book. I can choose my circuit levels that apply in my system. As you can see, these are the ones that I am utilizing. These are the conduit types that I'm going to use. So I'm just picking PVC schedule 80. And then you can also specify a default conduit size. So what is the typical conduit size I'm going to use for control cables? What are the typical conduit size I'm going to use for low voltage cables and power circuits and so on? So this is sort of the rule for building that Raceway, and this is the spacing rule from circuit level to circuit level again. So if I have a 4S circuit which has medium voltage power, then I'm going to separate it from my coax or phone circuit in order to mitigate noise. So that spacing is actually 12 inches. But again, this is a configurable rule book, so you can change it to whatever number makes sense for you. These are just default rules that we plugged in based on IEEE 518. 1977 standard. However, it was revised in '82, so that's really the one that we are using inside the program. If you have a similar standard that's more recent, or an IEC or CSA version, you can basically add it to the rulebook, or you can ask us to add it for you. So again, if I have 5 of these control circuits, I have 10 of type 2, and let's say I have 4 of my 4S circuits, and I'm going to go ahead and delete the rest out. So you can see that, you know, my arrangement essentially lands up looking like this. I'm going to use 3/4 here, and let's say I'm going to use size 5 over here, because that's really what I said is available for me. So if I look at my arrangement here, I can see the preview that all my low power control circuits are bunched up on the top, and they're separated significantly away from my power circuits. If I drop it, here's what the type of raceway that I get. And again, if you choose, you can select the conduits, and you can just you know, shift them wherever you want accordingly. If you need to move them closer, you can essentially do so. So there's full flexibility on how you build the raceway and how you actually move things around inside the raceway. So as far as the limitation inside the program is concerned, there's no significant limitation except the ones that are determined by the Neher-McGrath or the IEC 60287 method. Usually the limitation is just on the type of or the dimension type, or the ratio of the dimensions in the raceway. For example, the y by x, so the y-axis by x-axis ratios typically are 2 or 3, and not to really exceed those ratios, otherwise the equations are no longer valid. But those are the cases where the program actually warns you and tells you when the equations may or may not be valid based on the type of raceway that you're building, very similar to our ground grid system. But there's no limit to the number of conduits, the number of conductors. You can add as many as you like. This is a quick example of a data center raceway, so you can see all the air conditioning units, the crack units or HVAC units sitting on the bottom, the communication control cables, DCS cables, they're all essentially sitting on the top over here. And as we expect, the deeper the cables are within the duct bank, the heating effect will be greater, and the heat will flow from these conductors, affecting the cables above and propagating back into the soil. So we essentially radiate the heat out of the raceway into the neighboring soil in the system.